Remember that as well as another 14 online meetings this year, registration to many in-person meetings are now open. Take advantage of early bird registration rates, which are even lower if you're an Optica corporate member. Here's an overview of what's to come.
Optica will bring together the brightest and best in Los Angeles. Corner New York, Brussels, Glasgow, Sunnyvale, Paris, and Malaga.
Got my shades in the lab about 10:15. White coat cuff like a greaser again. Spinning that prism like a hubcap chrome, turning every photon into fuel I own. It's photonics. Baby, 2026. Riding in a light wave, doing new tricks.
From the lab bench to the factory floor, ideas move faster than ever before. Photon by photon, layer by layer, we're turning design into systems that scale. AI is rising, demand is real. Precision is now the industrial deal. Not just invention, not just the spark, but who builds the engines that run in the dark? We're crossing the line from concept to production time. We are the Global Advanced Manufacturing Alliance, building the backbone, the tools, the compliance, from wafers to systems, from roadmap to yield, turning tomorrow into something real. Step by step, we industrialize. This is where the future gets built at scale. Lithography, cushion, the limits of head motion and alignment in microns of thread. Design flows merging, electronic light, automation bringing complexity to life. Across the supply chain, signals align, from chiplets to packaging. Now is the time. No single player can carry the load. It takes an ecosystem to finish the road. The question is clear: who builds the infrastructure? Manufacturing Alliance, building the backbone, the tools, the compliance, from wafers to systems, from roadmap to yield, turning tomorrow into something real. Step by step, no compromise. This is where the future gets built at scale. Prototype dreams are not enough. Volume is where the world gets tough. Through every layer, tool, and line, we turn precision into uptime. We are the Global Advanced Manufacturing Alliance, engineering pathways to high volume science, from vision to fast, from concept to field, driving the moment where markets are sealed. Step by step, no compromise. This is where the future gets built at
It's time for the 2026 Optica Online Industry Meeting of the Global Advanced Manufacturing Alliance. Today we focus on a question that many in our industry are now facing. Who builds the infrastructure for heterogeneous integration? Across AI systems, advanced sensing, medical technologies, quantum platforms and chiplet architectures, innovation is moving fast. But scaling from prototype to reliable high-volume manufacturing remains the real bottleneck. That transition demands progress in tools, process flows, design environments, automation and precision assembly. That's exactly why GAMA brings these leaders together. Today's speakers represent the companies building the industrial backbone of next-generation photonics and semiconductor systems, from system architecture and lithography to design flows, motion platforms, thin films and automated packaging. And note, today's discussion is a pre-conversation ahead of our in-person Global Advanced Manufacturing Alliance meeting, June 2nd and 3rd in Brussels.
This is the bubble bar. This bar will be booked for Optica. The idea is that for those private meetings, private discussions that you make at the GAMA meeting, you have a follow-up discussion here. You sit down with those partners with whom you really want to follow up and you talk. You talk privately at the GAMA meeting.
With a reminder that this session is designed to be interactive, it's time to go live. This
Hello everyone and welcome to the Global Advanced Manufacturing Alliance Online Industry Meeting. It means the world to me to be here today in front of you to talk about a very important initiative that Optica is putting to all of you here. The idea is to make sure that we connect the companies providing different technologies for photonics and semiconductor manufacturing with the companies providing the tool, the infrastructure, and the end users of those technologies. Today is an online industry meeting, and it follows the standard format of our online industry meetings, which means we have two teams. We have the teams of integrators, companies who come here with a shopping list of technologies, and today is NVIDIA, ASML, and Senko. Wow, eh? And then we have the team of enablers, companies who have a technology that can enable some of the solutions the integrators are looking for. Aerotech, Vanguard Automation, Evatech, Synopsys, Keystone, and of course, everyone else with us in the Zoom room. This is one team, one event that follows the joint corporate initiative. If you are a company that needs to connect with potential partners, suppliers, customers, investors, or talent, this is my task for you. Go to optica.org and join corporate. Join corporate, become a corporate member of Optica. This event online today is only a prelude of the Optica Global Advanced Manufacturing Alliance meeting happening on the 2nd and 3rd of June in Brussels, Belgium. This is where we bring all our industry together focusing on manufacturing. This year, and Olga will explain this clearly, we have a focus on semiconductor manufacturing and technologies needed for the boom of AI. And of course, if you are looking for more meetings like this one, in 3 weeks from today, we have OFC and the Executive Forum at OFC. And I would like to give you some bad news. If you're still trying to book a booth at OFC, I am very sorry, but just a couple of hours ago, we sold out the exhibition of OFC this year. And also, I would like to say that the week after, we meet at Corning, at the headquarters of Corning in Corning, New York, to talk about advanced manufacturing of optics. Come to our online and come to our in-person events. And talking about online events, today is GAMA, but in a couple of weeks, in 2 weeks, we talk about 3D printing, right? 17th of March in your calendar. And with this, I would like to just say one thing. This meeting is live streaming YouTube. So for those of you in the Zoom room, look your best because people are watching you. For those people in YouTube, if you have any questions, comments, just write them in the chat and I will read them in the room. And this is, of course, also valid for the people here with me. This is, of course, also valid for the people here with me in the meeting. If you have anything to say, any chat, any question, any comment, please write them in the chat and we will give you the microphone and you will be able to voice all your comments. And with that, I would like to say that I have the honor and pleasure to give you a very important person at Optica. She's been for the last 3 years being the liaison between the GAMA committee, the Optica corporate members focusing on optics and optical instrumentation, and also she has been a person moderating all the online industry meeting focused on optics. I would like to give you the floor, our Director of Optics and Optical Instruments at Optica, Dr. Olga Ras. The floor is yours.
Thank you, Jose. Thank you very much for your kind introduction. Well, it was much more than I expected. And also, I'd like to welcome everyone and thank for our speakers and our attendees being here. I think it will be very interesting 90 minutes. And I would like to start with a little comment. I know that for some of those of the guests, of the attendees that followed Global Advanced Manufacturing Alliance since a couple of years, we started the initiative 3 years ago, you may notice that the focus has shifted. So for the previous meetings, we often concentrated on the wafer level optics, on the integrated optics, and also micro optics. And this year, the focus is different. But don't be confused, because Global Advanced Manufacturing Alliance, as it says in the name, it was always about manufacturing, most particularly about efficient manufacturing and lean manufacturing. And this focus remains always the same. What evolves is our emphasis. And this year, we decided to put this emphasis following the requests of our members on the topics where they see the real need, the real demand and interest. And right now, this interest is on the border or on intersection of the semiconductor and photonics. These two communities notoriously speak very less to one another, although many of the future solutions, especially for the very promising emerging applications such as data center connectivity, will have to implement both and photonics and semiconductors technologies. That's why we decided basically to use this opportunity to bring the two communities closer together, to talk to one another, for exchange the ideas. Because for the photonics to be truly efficient and lean, it needs to learn a lot from semiconductor manufacturing. And if semiconductor manufacturing want to cross the gap and reach into the new markets, it needs to learn a lot from photonics. And so this meeting and the one that will follow in Brussels is the first step. And I hope you will follow us on all the steps of this road. And without the further ado, I would like to introduce the first speaker of our meeting, who is representing the company that is really one of the drivers behind this transition. Liron Gans from NVIDIA. It's my great pleasure to have you in the room with us. Please, the floor and the attention of everyone is yours.
Thank you very much. I have to now follow the opening movie. That's quite a tough task, but I'll try. So first of all, I have to emphasize that I'm coming from NVIDIA research, and this is reflecting on the NVIDIA research work, and it does not necessarily reflect on NVIDIA roadmap. And unfortunately, I cannot comment on anything that is not publicly announced by NVIDIA in NVIDIA roadmap. But either way, when that's out of the way, I want to present you two approaches of how to scale co-package optics, and this is an open debate that we have in the community. So I hope that you will learn from it. So one of the approaches then what we call the narrow and fast, and the other is the wide and slow. And I will explain and show you the benefits of each one. And of course, let's remember that the name of the game is power. Here I brought some numbers on the power consumption of interconnecting data center. And of course, let's remember that any watt that is spent on networking is not spent on computing. And what we really want is computing. Networking is essentially necessary evil. It's a means to an end. So we want to reduce the power consumption. So that's, as I said, that's the name of the game, essentially. And when we are talking about the interconnect in the data center, we can divide this into two regimes. One is the scale-up network, in which we connect a few GPUs in the same rack. That's the geographical location, and they function as one big GPU. These connections are very, very high bandwidth, and up until now, they're being utilized by copper cables. when we talk on co-packaged optics and optics in general, we usually mean the scale-out networks in which we are connecting a few racks together across the data centers or across multiple data centers. And for that, of course, we need the networking. And as in the last, I think, year, we announced the co-packaged optics solution, and it is becoming more and more common in the industry. So the question is, how do we scale this? So there are a few vectors of scaling. So one of them is the time domain, in which we are continuing to increase the rate from 100 gigabaud to 200 gigabaud to 400 and so on and so forth. The other option is using more complicated amplitude or phase domain. So in the past, we worked in NRZ. Now we are using PAM4. We can continue to use PAM8 or go to coherent. And these two examples are what we call the narrow and fast. So narrow with regard to the wavelength. So we will use one wavelength, but we will modulate it very, very fast or more complicated. So this is what we intend when we say narrow and fast. There is another approach. We can use space domain, multiple lanes, or we can use wavelength domain, in which we use a lot of wavelength. And this is an example of what we will refer as wide and slow. Because if we have a lot of wavelengths or a lot of lanes, we don't necessarily need to modulate them as very fast, like in the first approach. We can even go back to NRZ and modulate them at the rate of 32 giga or even less than that. So these are the two opposing approaches. There is another vector of polarization. I put it in the middle because it only gives us twofold increase. But that's the main debate. Now, notice that I've put a brick wall in each one of them, because that is the limit of what we will encounter. So if we use more faster lanes, then we'll get diminishing energy efficiency. For modulation, we'll get diminishing signal to noise, and we'll see why. The power that we consume does not scale linearly. I haven't put a brick wall on the wavelength domain. That is a bit of a lie, because I'm actually dumping the problem on another sector, and this is the laser, and I will address it in a few slides. So let's see, and of course, my preferred way, and again, this is the work of NVIDIA research, is to go to the wavelength domain, and I like to quote Richard Feynman, there is plenty of room in the fiber, if we can break out of the ASIC. So that's the important part. So how does it look like? How is the architecture look like? So for the narrow and fast, we can use the same architecture that we use today. Today, we are using optical engines on an MCM. And this is roughly the way it looks like. And in order to scale that, we just need faster modulators and faster circuits that can drive them. For the slow and wide, we need to introduce an interposer. And that is, and so we are reducing the rate of modulation, but on the expense of packaging. So we need to add an interposer, which is not an easy task. This is how the link will look like. For example, we can use many rings and many modulator rings and many passive rings in the receiver. But we can see that if we do this, we can actually reduce the power consumption. And these are, and I put some references to show you that the interfaces there can consume less picojoule per bit. So these are the two opposing examples. So let's now dive in to actually what it means to do the narrow and fast versus the slow and wide. So let's take the case of 200G PAM4. So in the narrow and fast, because we are modulating it very, very fast, and we are using PAM4, the receiver sensitivity is not that good. So we need to use intensive FEC and DSP, which are major power consumption. If we go back and if we use the slow and wide, then we can go back to 32 NRZ, and then the receiver sensitivity is much higher. We don't need FEC and we don't need DSP. So we also save the power that they are consuming. With regard to the link budget, in the case of narrow and fast, we don't need muxing. In the case of slow and wide, of course, we need muxing, and that can cost us a few dBs of loss in the link budget. When it comes to circuitry, the narrow and fast has to have very, very fast circuits. So we need to use CMLs and we need to use very, very strong TIAs. In the case of slow and wide, we can go back to CMOS drivers and not so complex TIAs, so we can even save the power there. With regard to the electrical interfaces, in the narrow and fast, we have to aggregate the data a lot. So we need to use very, very strong SerDeses. So again, there is a power consumption and also latency, because the more layers of the SerDes, the more latency we add. In the slow and wide, we may need to use very light SerDes or no SerDes at all. So that's another saving mechanism. And of course, when we distribute the clock, distributing the clock at a lower rate is much more safe. It saves a lot more power. Now, and this is the main thing I want you to take from this my presentation. If you didn't follow me up until now, remember this sentence. When we go to narrow and fast, the burden is on the electronics, not the photonics. The photonics is already there. If we go to the slow and wide, the burden is on the photonics, not the electronics, because the electronics is very simple. We've already done generation where we modulated at the 32 gigabit NRZ. And as an optic guy, that makes me very happy, because there is a lot more room to improve in the photonics. We are merely scratching the surface here. So now let's talk about the laser. I told you that I'm dumping the problem of the wavelength on the lasers. So if we go to the narrow and fast, we still can use the single DFBs or DFB arrays that we are using today, but they just have to be very, very strong because of the receiver sensitivity. If we go to the slow and wide, we have to develop, or we have to put emphasis on lasers that can generate a lot of lines, which means usually that these are combs or module lasers. So this is one of the main challenges of the slow and wide. That's why it's not completely there. It's not there yet, but we have to put a lot of emphasis on these kind of technologies. And when I said there is a lot of room to improve in the optics, so we can add APDs instead of PDs, and they can give us more gain. We can use gain material in our manufacturing. We can use what we call a process-aware design, where we design devices that has less variation in manufacturing, and that can save us a lot in the thermal tuning. We can go in the electronics to more advanced nodes and save power there. And of course, we also talked about the clock distribution. So doing all of this, and we have a very nice paper on that, we can show you that we can go less than 1 picojoule per bit. And when we do that, we are even attractive to the scale up, not just the scale out. So if the scale up until today was done by copper cables, if we go below sub-picojoule per bit, we can actually be attractive and put optics in the scale up. So to summarize, two main challenges remains to the slow and wide. So first is the packaging. We have to use interposers, and this is not a simple thing. Of course, interposer today exist because we do have 3D integration in other sectors, but not in optics. So we have to work on that. The second, we have to work on the source. We have to enable comb lasers or modular lasers to have a lot of wavelengths. And as I said, we can introduce a lot more improvements in the optics. And I will repeat what I said. The main thing is if we want to go slow and wide, the main burden is on the optics, not on the electronics. So we have a lot more to improve there. And with that, I'm finished. So thank you.
Thank you very much, Leon. That was a very quick but very insightful presentation. So when I always look at the two approaches, I believe it's clear, as you described, right, that there are bottlenecks at both of them. And some of these technology bottlenecks, but others, right, when we're going into this, when we start to think about bringing the systems really into the real life applications, it's also supply chain. So how is it in terms for the both technologies for the readiness of the supply chains to support one of the two approaches, or the both approaches?
So let's start with what I've already mentioned. So in the supply chain, for the slow and wide, we need comb lasers. So we need to encourage companies to make comb lasers a product ready. That's one. The other thing is the packaging. We need the interposer. That's a game of the big foundries, TSMC, Global Foundry, things like that. I think these are the main challenges in slow and wide. The narrow and fast, the emphasis on the supply chain is on faster modulators. So TFLN Mach Zenders or TFLT Mach Zenders, and so on and so forth. I think that's the main issue when it comes to the narrow and fast.
Would you consider if you compare horizons, because very often one technology doesn't go to mass adoption because it's just not, it doesn't have the technology yet. So what maybe would be theoretically from your point of view the horizons for either one of them or one after another to go really into the adoption?
So again, what I'm saying is my personal opinion of how I
Yes.
see this. So I see that we will go to narrow and fast for maybe one more generation, two. Then we have to go to the slow and wide because the electronics will not support it anymore. So, and again, it doesn't have to be a clear cut. It may be some intermediate, so like 4 wavelength, 8 wavelength, and not as slow a rate as 32 giga, maybe a bit more, maybe stay in PAM4. But I think that as we go to the next generation, we will move more and more to the slow and wide.
Thank you, Leron. We have a question from Philip, Keystone Photonics. Philip, please unmute yourself and ask the question.
Yeah, so in the last sentence, you actually went towards my question. So my question is, you talked about a lot of things that one could do and what the pros and cons are. Can you be even more specific on what you are going to do? Can you give us a roadmap?
So again, I cannot talk about the official roadmap of NVIDIA, but I can talk about what we see in research. So what we do in NVIDIA research, and that is to help the product or to eliminate or de-risk what they are doing. We are definitely going and even now presenting work on slow and wide approaches.
I see, but I just would like to make you aware that we as an ecosystem can prepare for different approaches. But if you're not specific or you dare not being specific on what track you'll go, once you went there, you'll find that things are not prepared and the technology has not been developed.
Definitely. I agree with you. I'm just saying it's not my job in this forum to say this. When the product. When the guys that decide the product will decide on on their preferred approach, I'm sure that the ecosystem will know about that.
You show them the possible ways,
Exactly.
but it's up to others to decide which way they decide to go. Well, Philip, you will be at the OFC. I believe there will be quite a few discussions on this. Leon, I wanted to ask because you also look at when you design the system, you look at it in its entirety, right? It's not only optics, it's not only photonics, it starts to be electronics, it starts to be heat dissipation problems. It starts to be, right, the connections to the electronics. So how does this, when you look at the complete analysis, what are maybe the let's say the bottlenecks or the limiting factors for the complete analysis of the unit as a system?
So definitely heat dissipation is a major issue, and as we go, if we continue in the narrow and fast, this will become more and more a problem because the higher rate you go, the more losses you have. Every loss that you have in the system goes to heat. So you have to somehow take it out. And so that's why I think that even from these aspects, the slow and wide will be better.
Thank you. We have another question from the audience. J.S. Kim, please unmute yourself and ask your question. From Panoptics. JS? Okay, no reaction, then I will read it out. In some cases, new and special redesign might not be enough to make uncooled operation when it needs higher optical power with stable wavelength. How do you think about it if someone may say the minimal thermal method, microtech, can be considerable? What?
I
Okay.
also
How do you think about it if the minimum thermal method like microtech can be considerable? I
you
don't
mean
understand. I read it from the chat. Jace Kim, are you here? Would you? So, okay. Okay. So it's an excellent answer. My family is asleep. I believe it's rather in direction, of what I asked you about the heat dissipation, right? Where it
yeah.
becomes.
So of course we're looking at every direction, especially in research. We're looking at every direction of how to cool the system. So much beyond just water cooling or air cooling. So definitely, if I understand correctly, the question alludes to more microsurfaces and things like that. So yes, even that is a valid way that we are
Thank you so
interested in.
much. And yeah, I would like to use this opportunity to really maybe since we started to speak about really system architectures, to bring the next speaker into the room, Ahsan Alam from Synopsys, to maybe give a couple of his comments on the designs which Synopsys are very famous for. Thank you so much, Liron, and Ahsan, it's your turn.
Yeah, thank you, Olga. Let me share my screen.
Yes, please.
Okay. Okay. I hope
Yes,
I'm on the right screen.
it's
Okay.
here.
Okay. Yeah. Thank you. And first of all, thanks a lot to Optica for organizing this event. I think we're already off to a great start, thanks to Liron as well. And I can see that it's going to be a very interesting discussion today. I will try my best to make some contribution as well. So when the topic for today's meeting came up, I thought that, even though Synopsys has different businesses, we have IP business, we have EDA solutions. I am primarily from the software side of things. So obviously, what I'm going to talk about is more from a design point of view, that how, we can provide solutions that will help with a lot of the challenges that maybe Liron already brought up and Olga has been talking about as well. Things like, how do we account for the heat in the package? How do we bridge the gap between the electronics and the photonics? How do we design a system as a whole so that everything works at the end of the day? So with that in mind, I restricted myself to 2 slides. So the first slide is going to be a very high-level overview of the different types of analysis that you need to do when you're designing a package like this. So by a package like this, I mean that it's typically a 3D IC package where you have a photonic die inside it, and then it becomes a co-packaged optics type of product. And so when you have a system that has this type of dense combination of multiple dies all stacked on top of each other, there are different solutions that you need to go to before you can have a full product. There are lots of blocks here, so I'll go clockwise maybe from the bottom left. Of course, you need to care about the photonic integrated circuits. So I actually have a slide for that next. And that's always have to be there, right? I mean, we are bringing in photonics as a key enabler for these systems. Going clockwise, up there I have optical input output. So one thing that's very different between say a pure 3D IC electronic system versus a co-packaged optics system is the fact that you have these fibers coming into your package, and getting the light efficiently in and out is very critical. As Liron mentioned, the name of the game is power. You want to reduce the power loss as much as possible. And so if you are incurring loss as light goes from your chip to your fiber, that sort of defeats the purpose of bringing the photonic chip onto your package. Unfortunately, as you bring the fibers into the chip, you have a multi-scale system at your hand. Like you have these nanoscale on-chip couplers versus these macro scale, lens and fibers. So you need multiple tools to work together so that you can design the whole system. There's also the additional challenge of heat and stress getting generated in the package that can cause deformation. So you need to couple these solutions with tools like mechanical so that you have the deformation simulated first, and then bring that into the optical domain to figure out that in an operating condition, will there be any variation between or misalignment happening between your lens fiber and your chip. And you need to be able to account for that at the design scale so that you can have that tolerance built into your system. Next, thermal, a big thing. I mean, we've already talked about it multiple times today already. With everything coming together in a tight package, things get heated up. You need to be able to have solutions that allows you to build that whole 3D geometry and then run thermal simulations. So we have tools like Red Hawk SC Electrothermal that we have been working with foundries to get certified at the advanced nodes, and then build in the capability so that they can take in the different layer stack information and GDS information for multiple dies, create that sort of like a reduced order model for all the different dies. Because when you're doing thermal simulation at such a massive scale, you have to do some reduction in this in the definitions, right? So you create these reduced order models for all the different dies, and then you use again maybe definitions coming from the foundry, for example, like 3D blocks, to stack everything on top of each other, and then you can go and run the simulations. You get a full thermal picture for your system, and then that temperature can then go into other simulations, right? If you're doing electromagnetic simulation, that could be affected by the thermal map. If you're designing your photonic circuit, that performance could get affected by the temperature. So this thermal simulation then go and feed everything else. You see iSpec there as well, which is a software that can allow people to run simulations at a much larger scale, like at the system level. And that's important for maybe the question that we already had in the chat, right? That how do you account for cooling? And so if you want to account for cooling, then you have to go to the system level and bring your coolants, your cold plates and everything into your simulation. So multiple tools might be needed, right? At the package level, you do some kind of simulation, but then you transfer that knowledge to the system level, and then you design your cooling system around it. Next, we have signal integrity. When you're designing your photonics by itself, you don't really care about what's happening around it. But as soon as your photonic die goes into a package, there's so many other connections, the ball grid arrays around it, above it, the metal traces bringing the signal from the driver into the optical switches. All of these can incur additional loss and distortion to the signal. So you need to be able to run electromagnetic simulations with tools like RaptorX, figure out what is the electrical S parameters for all of these, for example, and then bring them into your simulation. We have power integrity and reliability, which is very common for people doing electrical designs, right? Tools like Torem and Red Hawk SC have been used for a while. But now photonics is coming into play, right? So we have developed new workflows where you can combine the electrical and the photonic die together to create that multi-die stack, and then perform IR drop analysis or electromigration analysis. The heaters might be drawing a lot of current from your EIC, and now since the path that the current goes through consists of multiple dies, you need to be able to model all of them together to do a proper reliability analysis there. Similar thing goes for ESD, right? Again, when you have multiple dies stacked on top of each other, the discharge path is different, and it's again complicated, involving paths that belong to different dies. So again, you need solutions where you are able to take these different dies, stack them on top of each other, and then perform this type of analysis. And then last but not least, I have structural. So I think Liron already mentioned this, that one big problem with the slow and wide would be the interposer. And so that's where tools like mechanical comes in, that you need to be able to build that system with your interposer, perform structural integrity analysis, and make sure that that huge interposer is able to support all those dies that will be sitting on top, and so that you can go and confidently manufacture it. With that, I'll go to the next slide. And so here, I at the beginning, I just have the traditional, photonic circuit design path. So you have, in photonics, we all know that you typically need very high performing components. So you start at the bottom left there, where you have your layout tool, you're designing the P cells for your different components, in OptoCompiler. And then you bring those layouts into numerical multiphysics tools and optical tools to run simulations, optimize their performance. Once you have done that, you create compact models for them. And these compact models need to work with, maybe the off-the-shelf components that are coming from the foundries. The foundries are already offering comprehensive PDKs, the big foundries are. But when you create your own compact models for your own custom design elements, you need to be able to put everything on the same schematic and then be able to run the simulation. These models need to be able to talk with each other. And that's something that we have enabled by working with foundries using CML compiler. And then so finally you go to the circuit simulation stage. Right here, there could be different solutions available and needed, because a lot of the designers are coming from pure photonics background and they prefer tools like pure photonic simulation tools like interconnector OpSim. That's the environment that they're used to. So we need a solution where we can allow designers to sit in these environments, design their photonic circuits, but then once they're ready to hook it up to a real CMOS driver, they can go to an EDA environment in tools like OptoCompiler and then run an electro-optical simulation that models the CMOS driver and the photonics accurately, and then allows them to do an electro-optical co-simulation. Once you're done that, then the rest of the flow is not very different from electronics. You do SDL, LVS. Once you can do back annotation to bring the routing information back to your schematic and run simulation again, and then you go for tape out. Now, what's different here is the pieces from the previous slide needs to come into this flow, right? So the tiny blocks that you see at the bottom, we already talked about it. The mechanical simulation that we are doing on the package, for example, that could give you a stress map, and that stress map can go into numerical to show you that, if you have stress buildup in your system, if you have a big MZI in your circuit and there are different paths that are experiencing different level of stress, you could have a change in the performance of the MZI. And you need to be able to account for that at the design stage and not, once you have fabricated it and then you see that, okay, it's not performing according to spec. Similarly for thermal, once you have that temperature map, that can go into your component simulation, that can go into your circuit simulation. You bring it into your schematic, your layout aware schematic. Every component sees what temperature they're going to see in the actual package. And then they tell you that, what their performance is going to be. And I think I already mentioned that, for signal integrity also, you can bring in the information about all the different connections that will show up suddenly at the package level. So you can bring that to your schematic as well, and then run a simulation that will tell you exactly what will happen to the signal integrity once your peak goes into the package. So with that, maybe I will finish my presentation and we can have a conversation now.
Thank you, Hassan. Thank you so much for such a detailed analysis for the simulation flows. So, when we asked Liron about his view on what are the bottlenecks, his approach is system and approach of the really components and integration. From your point, as the basically provider solutions for the simulations, are there still like gaps that in this multi-physics simulations that needs to be overcome to be able to reliably really simulate the co-packaged optics and the solutions with integration, or is the flow ready?
Yeah, no, I mean, obviously the marketing pitch would be that everything is ready, right?
Let's forget the marketing pitch.
The reality is that all the different blocks that I showed, I believe we have the right solution for all the different pieces, right? If you want to do structural integrity simulation, mechanical is a pretty comprehensive tool. You can put in anything in there and, you can run your simulation. In terms of bottleneck, I see two bottlenecks. One is within our control, which is the communication between the different tools. You can run very accurate simulation in different multiphysics domain, but then you have to be able to efficiently transfer information between them. Right now, we have that capability, but in a lot of cases, maybe those capabilities are static. And kind of like, as the industry is moving forward towards like, more reliability type of questions, or, what will happen as a product goes into a real environment and runs for, a year or two, what's going to happen during the operational time, any transient effects that's coming in. So we need to be able to have a dynamic link between a lot of the simulators. That's something that we are working on and we will work on. The other bottleneck that I see are coming from the ecosystem, that in a lot of cases, foundries cannot share the information with the customers freely. There's encryption involved. So you need to be able to take in those encrypted files into your tools and then still allow the designer to set up the structure properly and be able to inspect it if there's any issue. So that's always a challenge that we work with foundries to make sure that what can be shown and what cannot be shown. In a lot of cases, maybe there's a workflow ready, but the foundry doesn't really have a final version of the technology file that they need to provide to the customer. The technologies are still evolving. So when we work with customers, maybe they get a file from foundry about a certain technology, but then, once they have designed something, maybe the foundry process has already changed because it's still in fine tune. So those are, challenges that are maybe part of the growth pain, and it will eventually settle down, but that's still a bottleneck right now. Yeah. So and then I think the last piece is the different companies that are supporting each other in this co-packaged optic ecosystem. So you have your system level designers who are depending on vendors that are designing the individual blocks. And in a lot of cases, when the system level designer is doing the system level simulation, they need to have these behavioral models maybe of these different building blocks that would come from the vendors. And so there's maybe lacking there as well to enable the vendors to create reduced order model that protect their IP, but at the same time allows them to give something to the system level designer so that they can do the simulation at the system level. So yeah, I think communication between foundries and customers or the different vendors, that's kind of like, one challenge that we still have to solve. And then within ourselves, better communication between the different tools.
This is what we also try to solve with the Advanced Manufacturing Alliance, the communication. The different vendors and providers talk with one another and agree on the standards and basically how to work together. As an also question maybe from the side how many of the different types of the connectors, or let's say types of integration, you're able to simulate, because there's such a variety of different technologies, right? How the things can be integrated together through the wire bonds, through the direct bonding. What a selection of the PDKs you have for your simulation tools?
So when it comes to supporting PDKs, I believe Synopsys has PDK support for most of the key foundries that are working on co-packaged optics. I'm new to the Synopsys world, I guess, because our acquisition just went through late last year. So I am not 100% sure, what's public and what's not right now.
Okay.
So I can't say any names. Of course, as ANSYS, we had lots of press releases with TSMC. So maybe I can kind of just share what we have in the press releases. And so that kind of already talks about this kind of software companies working with the foundries to create sort of these reference flows, right? And so these reference flows are documents and examples that show that if a customer wants to use a particular foundry technology, how do they set up their simulation? And what sort of file do they need from the foundries, namely the tech files and material information and so on, right? So that's kind of what we are working with foundries to create these standardized reference flows so that an end user simply grabs that reference flow, they get all the necessary files from the foundry, and then they can simply go and start their design.
Okay. Would you be able to simulate wire bonds?
We can, yes. Yes,
Excellent.
we can. I mean, it's gonna be a big simulation, but we've not very recently, but not too long ago, we enabled FDTD on GPU, right? And that gives us a lot of capability to run huge simulations very quickly. That was not possible before. So you can take a photonic wire bond into FDTD and then run a full 3D simulation now. It'll take up a lot of Liron's GPUs maybe, but you will be able to run that simulation.
Well, then let's go from, thank you so much, Asan, and then let's go from the
Most welcome.
simulation to practice, and we'll hear from next speaker, Vanguard Automation, Laura Horan, that will talk about practical and real-life wire bonds. Laura, you're welcome to the floor.
Thank you very much. I think it's clear the message from the industry that there is a real demand for advanced photonic packaging. I think we're grateful to NVIDIA for sharing the vision and also to companies like Synopsys for showing us what our design needs to look like. But the question still is, how do we have a manufacturable solution for the next generation of photonic devices and designs? And how do you make it automated and repeatable and ready for high volume? And I think we see also that the question has changed from if it's possible to do it to, how many units can you produce per month? This is the big question right now. And here, Vanguard Automation have a part of the puzzle, a piece of the puzzle of the solution with photonic integration. And what we do is we use 3D laser lithography to fabricate optical elements onto optical components to do the photonic integration and to ease this process. So you see in my slides here, 3 pictures on the top, and they show our solutions. The 2 pictures on the left show photonic wire bonds. These are basically 3D freeform optical waveguides used to connect 2 optical components together, doing mode field matching and also using the alignment tolerances. And the other solution is micro lenses, seen in the picture on the right-hand side. So here we can fabricate in situ micro lens on the surface or edge of optical components for beam expansion, spot size conversion, and collimation to really relax alignment tolerances and to enable passive alignment of photonic components. So what I want to actually show you in these slides is a solution that our industry partners, Sumitomo Electric, have worked on to bring 3D laser lithography photonic integration to co-packaged optics. So you see in these slides on the left-hand side a typical schematic of a co-packaged optics with a glass interposer. So we have fiber arrays connecting into the glass interposer, then connecting to photonic integrated circuits. And their challenge here was to do the photonic integration from the glass interposer to their photonic integrated circuits. So the picture in the center here from Sumitomo Electric, this shows a flip chip packaging for a PIC to a glass interposer. And it shows here using vertical coupled beam expanding lenses to do the coupling to ease the alignment tolerances of the coupling of the PIC to the glass interposer could be done passively. So what happens here is that the light, when it comes to the glass optical interposer, gets expanded out by a vertical coupling beam expanding lens to a secondary beam expanding lens, and this really relaxes the coupling tolerances while keeping the low loss that we need for optical loss budgets. And the second example on the right-hand side here, this is a similar example, which has edge-to-edge coupling and using photonic wire bonds for the photonic integration for a glass interposer to chip. So you see in the top right-hand side of the picture, the glass interposer, and a photonic wire bonds doing the mode field matching and coupling this to the chip, which also has an angled facet, so it's an extra complication for photonic integration. You see here, because the photonic wire bond is a freeform optical waveguide, it can easily connect the 2 components together, doing mode field matching and compensating for that angled facet. So in general, Vanguard Automation is really bringing the technology of 3D laser lithography for photonic integration to a high volume manufacturing state with our machines, materials, and processes. And
thank you, Laura. Thank you so much. I'm very happy that already in your intro you mentioned about passive alignment, because now I don't feel that bad about asking it. So how do you think, how much of the really alignment optimization can realistically move from active to passive, and maybe in which horizon terms?
With our technology, everything we do is passive. We do everything passively. We have no active alignment when it comes to using Vanguard's automations, photonic integration. I see there is great scope for really bringing passive alignment to high volume manufacturing. And actually, it's the direction we need to go in to really get to that high volume and scalability for photonic integration and photonic packaging. So I see it as a must. And when we look at the current situation where we are doing active alignment of individual components and using epoxies to glue into place, this simply takes time, time that is not there when we want to go scalable and produce hundreds of thousands of photonic devices a month. So I definitely see this as the future.
How do you see opportunities for improvement the speed, because it's a laser lithography, so it's still it requires it's longer in comparison to some other processes?
Currently, this is a piece by piece fabrication process. I see there's definitely ways to make this highly parallelized as an integration process, but that's for the future.
Is it rather in the direction of integrating several basically lasers in parallel, or other ways of parallelizing the process?
If you look at the literature, there are multiple ideas in place to do this. So one application is having multiple lasers. One application is using SLMs, spatial light modulators. And there are also other solutions out there to bring the technology forward.
So what would be, let's say, if we're looking ahead in the 2-3 years, what would you see that will be the productivity? What would you hope to be the productivity of the 3D laser lithography?
I think we're going to see units where we're producing hundreds of thousands of units per month using laser lithography. I think this is clear the path forward, and there's so much research and development work in this area that we will definitely see this.
Thank you so much. Thank you for your comment. As I don't see, thank you, Laura. I believe we don't really have a question from the auditorium. Maybe someone of the speakers are interested to ask a question. If that's not the case, then let's move slowly one level deeper from the system integration to actually wafer integration. And then I would like to introduce to the floor really the speaker who has a lot of the expertise in this field. It's Henk Niesing from ASML. Henk, the attention of everyone is yours. What does ASML prepare for the advanced packaging?
Thank you, Olga. Sure. Let me share you. Do you hear me and can you see the screen?
Not yet.
Share.
Now it's coming. Now we see all of us, and now we see the screen. Please move to the, yeah, perfect.
Okay, thank you. Yes, I'd like to give you an update on ASML lithography, and obviously for us, photonics is at the heart of our machine, of the heart of our soul and everything. We live on photonics, and we use the photonics to print integrated circuits in the semiconductor world. And I'd like to share with you today how also such a machine could be of use for 3D integration as well as producing with photons photonics chips. In just one slide, a short and brief, the roadmap in semiconductor world is obviously all geared around Moore's law of continuously scaling, bringing more transistors on a square centimeter. And it is all driven by scaling in areas of logic and memory. And both logic continues on the transistor designs to bring it tighter together, as well as memory, new design structures, and ultimately also integration in the vertical direction. But in addition to scaling in 2D direction, it's indeed now in the last era, there's an era of integration happening where chips, both logic and memory and photonics, are brought together in the vertical direction of integration. Now, having a look at that one, as mentioned already by the other speakers, interposers is a key where multiple chips, like in this example, chips of a GPU, a CPU processing units are brought together with memory, DRAM, SRAM, as well as photonics, all put together on a single package. And in this case, brought together onto a larger interposer. Now that 3D integration is something that, in terms of the lithography machines, ASML has introduced a new system to support this larger integration of multiple chips. Because obviously, bringing this all together, you start to get into an era where you become a fab of chiplets, where all chiplets of different sorts will be combined together in one package. Both DRAM, the interposer itself, photonics ICs, chiplets, CPUs and GPUs, all brought together in what we call advanced packaging. Where all these chips are brought together is indeed a challenging operation, where a lot of things like bonding will take place, but also precisely bringing those chips on top of each other with a very high precision and overlay accuracy, correcting those fingerprints. That is all capabilities that were built into the lithography system to allow this kind of packaging vertically. Now for that, recently, end of last year, we introduced a system to the world where you now have the ability to print such an interposer layer all in one instead of stitching it together. So we came with a larger I-line-based scanner with a much larger field size that allows you to print all in one the interposer layer. That brings, of course, the interposer layer, but also other applications around 3D chiplets with photonics, because this system comes with a very large depth of focus, printing the micro bumps, bonding the pads, the HBM pads. This will really revolutionize and change because it comes with a larger field size, and hence it comes with a much faster speed and bringing the cost down to print and produce the packaging. That's on packaging. The other topic is around photonics, and no need to introduce photonics as the new kid on the block to bring lots of improvements in terms of latencies, bandwidth, power reduction in areas of data centers, but also the future of healthcare and quantum computing. How photonics comes together also in terms of patterning photonics chips is quite different from patterning a semiconductor chip. And if you make a short summary about the challenges that we see on patterning PICs, we see it in different areas. It comes obviously with areas of, we're dealing now here not just with silicon, we're dealing with many different sorts of material that has to be used. Different substrates, different materials, bringing challenging to do the patterning properly. But also topography you're dealing with large topographies, like you try to put the fiber together with these V grooves. You need to have very large depth of focus on your lithography system to handle that topography. The other part is CDU and line edge roughness. Photons are, of course, don't like rough edges, as some people say. They have to be very smooth, as opposed to the electronic lines. So CD uniformity and line edge roughness are very key to reduce the amount of losses in your signal. Lastly, also for photonics, overlay is a key item. If you want to stitch multiple chips together, the stitching has to be with a very tight overlay. Now, if you then take the scanner, the lithography system, and you look at the focus of ASML is to really bring your resolution obviously down to levels where you need to have the resolution, down to 100 nanometer in terms of resolution, typically for photonics chips. But we also see the key is to bring the CD uniformity down. And to bring the CD uniformity down, it's a matter of changing the wavelengths, so going from an I-line system to a KRF, to ARF, to immersion systems, and also bringing up the numerical aperture, the NA of the system. And the Rayleigh equation will tell you that will bring your resolution down to the levels where a typical domain of photonics integrated circuits are. So here you see the indication of how the resolution has improved over time by introducing these new technologies, the new lithography systems with the new wavelengths, smaller wavelengths, but also the size of the bulbs will tell you about the absolute CD uniformity that the system is capable of producing. And that, with introducing scanner technology and bringing better in terms of optics, we've been able to reduce that CD uniformity drastically, and that will lower your line edge roughness significantly. To levels of, if you look at the far right side here now on immersion, with a specification of 3 nanometer CD uniformity, we're seeing champion data of a full wafer, over the entire wafer, a 3 sigma of CD of 1.3 nanometers. And that really is the drive where you'll be able to see photonics lines printed, which have a very low loss in terms of light. Now that obviously is a challenge because these machines are also expensive. So also ASML is taking the holistic lithography approach and also is exploring all ways possible to minimize and reduce CD uniformity and line edge roughness by all means around the machine as well. And I just brought to you one example, and that is with software on the OPC side, on the mask side. So to optimize the mask where the lines are, the designs are, the company that's called Brian, that is part of ASML, delivers software that allows to optimize the lines on the mask such that where traditionally you will have a line which have quite some roughness, with this new type of optical proximity correction called curvilinear OPC, we're able to bring those lines much tighter with a much better edge placement error or CD uniformity. This just to illustrate that taking the exact same machines on the left side, on the right side, you can already improve a lot on the photonics yield and performance of the chip itself by optimizing the designs on the mask. Now that's on photonics. What we also see, and that's what we're, it's a very nice picture to say that photonics is very much alive. We're talking with a lot of companies that is planning or are already manufacturing photonics of all sorts. And we're happy to collaborate with many of those, but it also means we have a very diverse industry that requires very good collaboration if we want to accelerate photonics and the integration with semiconductor. And that brings it also to my summary. We obviously see a huge uptick in demand for chips thanks to the AI coming into the world. We hope to bring and support this with new lithography solutions addressing this market, but not just the machines itself, but also the holistic lithography solutions. And in the end, it's a call for the entire industry to really understand that with collaboration, we can really scale and accelerate this, which is much needed. It's been in the semiconductor in the last 30 years, the key to success of collaborating and understanding each other's strength. That brings really an acceleration and things to scale. With that, thank you.
Thank you so much. Thank you so much, Henk. I mean, this is this is a big change, actually. I mean, it's in the way of doing it. Let's go first to David Dawson from Material Insights. David, could you please unmute yourself and say your question yourself? David?
There, can you hear me?
Yeah, I can hear you now. Yeah.
Oh, so my question was for the packaging. Does ASML see a trend towards packaging at the wafer level or at the panel level for the advanced interposer?
Yeah, we see it both right now on the wafer level, but we're also gearing up towards being ready to offer lithography for panel level on the interposers. Yeah, that's definitely a trend. Yeah.
with the submicron dimensions that you can easily achieve in a wafer scale?
Yeah. Yeah, so basically being able to have it with the identical performance, yeah.
Oh, very good, thank you.
Hi. So, and we have Mark. So, Mark, could you please unmute yourself? You can ask yourself. Welcome. Thank you
Yeah,
for
thank
coming.
you. Of course. I was curious who the customers are for the XT260. I know the typical customers are Samsung, TSMC, Intel, those types. Is it a similar customer base or are they new entities?
There is the similar ones, but I think obviously advanced packaging is also entering into the OSATs, the pure play packaging companies. But also with the larger foundries that do advanced packaging themselves. But also that same system is also start to be used for in the photonics area, in the engineered optics to make the smart glasses. Also there you have to have a very large field to be able to have that single display on the smart glasses. So you see it being attracted by different markets. Yeah.
Thanks.
Yeah. So there are a lot of things happening here. So one of the things is what is like how sensitive is going to be the system to the nanometer level to the nanometer level drift. I'm talking about the drift, in a short period, like let's say 24 hours.
Yeah, it's I could spend the whole day talking about that. It's of course something we think we master because we're doing this now for 30 years in the semiconductor industry.
Yeah.
To bring absolute stability we are doing overlay performance at nanometer levels at speeds of 300 wafers per hour. So it's and again, thanks to a lot of optics, you have to do extremely good alignment. You have to level the wafer very well. It's all done with optics and with photons. So
yeah. So the other thing is like there is this recent news from yesterday, and it says ASML unveils EUV light source advance that could yield 50% more chips by 2030. So what is can you comment about this? This is this is big news.
yeah, and you're very on top of the news. That was yesterday. Yeah, so it's indeed. You may recall that ASML has been working for the last 20 years, bringing EUV lithography to life.
Yeah.
In the early stages, people thought it would not be happening, and people were voting in the industry. Would it happen, yes or no? It was so extremely difficult to make a source that could produce the EUV light.
Yeah.
And that has taken us a tremendous amount of investments and people, and we have brought that obviously to light. EUV is in high volume manufacturing right now. But still, we see the very key, and I think that's for photonics as well, the key to really bring your cost down is to bring your productivity up. And for EUV, that is bringing the light source to a level that it has such a high power to produce and bring it to levels where you run 300 wafers per hour on an EUV tool. And that's thanks to the high power EUV light source. Yeah.
Yeah. So if I ask you like what is absolutely non-negotiable in the systems respects to the laser parameters, what is it?
I think many parameters, but maybe back to your first point as well, it's all about stability as well. You not just have to have one pulse doing the right thing, you have to have the 50,000 pulses per second to do the right thing.
Yeah,
And
yeah.
that is stability is of course in the whole technology of such a machine is a tremendous task. Stability in temperatures, but also in terms of alignment, leveling of the wafer. That's probably the key challenge. Yeah.
Yeah. Well, many thanks. So, and any questions, I mean, that you have, please continue posting in the chat. There is something about this is testing and probing determine whether the upstream precision actual holds. So someone that could help very a lot with this is Philip Dietrich from Keystone Photonics. So Philip, could you please take your presentation? The floor presentation is all yours.
Right. Yes. Thank you very much for the kind introduction. So I'm Philip from Keystone Photonics, and we're basically there because photonics has no perfect yield. No production technology has perfect yield. Despite all the efforts of ASML, you need to test photonics. And what we basically do is we use 3D printed micro optics, as you can see here, that is functioning as a probe. Well, in this marketing image, where this probe is simply focusing on our production location in Karlsruhe, but this gives you a bit of an idea what we're doing. So all this thing here is about as thick as a human hair, and we use this to probe wafers. You may have heard the recent news that Form Factor in Livermore has acquired Keystone Photonics. So we've been working for about 6-7 years together with Form Factor, and now we're one company. So if you look at the globe, Form Factor sits over here in Livermore. They have production locations in Dresden, and we're basically now targeting the volume market, and that is actually the reasoning behind this acquisition. We want to provide turnkey solution that not only allow customers that are willing to invest in test capabilities themselves, but the whole community has access to our technology. So basically the idea is to provide turnkey solutions that work from fabs, that's basically provided by system level testers, to volume production. We will continue to serve the market, so that also includes competitors, form factors. So we're still free to operate. And another big reason is, of course, that we have capacity to ramp. We have clean room. We buy more machines. If they're interested in that, I'm happy to go more in that direction. Now, let me talk a bit about what we are actually doing. And after the talk of NVIDIA, I changed my slides a bit to get the input I want. I cannot wait for it. So let me guide you first through what we are actually doing on the technology level. So this is a prober of Form Factor. You see here the probe arm. This is objective lens to look from top. This is a hemispherical electrical probe card. And we're basically providing this metal piece here in the front that is used for optical probing together with electrical probing. And what this does, it either penetrates trenches on wafer level. So you etch a trench and you can actually probe edge coupled devices, or it looks at grating couplers, and that's something we heavily invested in, that we can test expanded beams. And that's the most important thing for CPO. So if you look at CPO, insertion 1 is a grating coupler or edge coupling, depends on the implementation. Insertion 2 is at wafer level, but an expanded beam. And we're capable of testing these expanded beams. We're not only capable, we're doing this. We're serving 2-digit prober numbers at a single customer right now. So to summarize, our technology is capable to probe trenches, gratings, and expanded beams, so everything you need for CPO, all insertions. We are in production now. This is not fiction, or we're really serving to all major silicon photonic foundries. We're serving to a broad range of end customers of the CPO ecosystem. And we can test, as I said, the current CPO implementation. And now that's the reason, that's actually the thing what interests me most, like where is that actually developing here? So this decision, for example, are we going to a lot of channels, or are we going multi-lambda? These things, they have impact on our roadmap, and I really want to know this, and I think it's beneficial to be transparent on this. So I actually added this request form. So everyone who's interested in giving us input, You can, for example, vote for a channel count. We can currently do a channel count of 64 channels. If you want more, put a high pro here. Contact me, please. Get in contact, and we can really adjust things. We know what to do to scale these parameters up. For example, we can go up to 656 channels, but it's not done just like now. There is effort to be put in. And that's a similar things with pitch. We can do 80 micrometers today, but maybe you need less. Or wavelength, we probably get there. It's OCL already. Or power. If you use a lot of lanes, you may need higher power than what we can do right now, which is 25 dBm. You may need more polarization PR, so polarization extinction ratio, or lower reflection, or you need to have shallow trenches, or you need to have also, if you need less angular variation than what is right now in the market, yeah, please approach us. So that would be extremely helpful, and we're committed to working in that direction.
Yeah, thank you so much, Philip. I mean, you made my day. This is like, adapting the technology as soon as it's happening. This is great. And this is a very valid question. I mean, this is something that is repeating. This morning I just hear Askar talking, and it was this question is repeating, and we still don't have a straight answer. That's one of the things, and I totally agree with you. So that's very good. Thank you so much. Thank you so much. You really made my day. So we have all the way from Copenhagen, Henrik from SPIO. So Henrik, could you please unmute your mic and open your camera and tell us your question?
Yeah. Hello. It was more to the ASML presentation about how to mass producing waveguarding instead of making one by one, so we can replicate the waveguard structure on a different platform, whereby nanoimprint.
So, Henk, can you answer that?
Oh, sorry, I was on mute.
Yeah, we couldn't hear you. It's like, what is Henk?
It's not over yet. Here.
No, it's good. Indeed, nanoimprint, there is several technologies that we talked about laser lithography just now. Nanoimprint is another form of lithography where waveguides can be produced. I think, and that's obviously demonstrated as well. So comparing the different lithography solutions, I think it comes down to to things like yield and stability. We talked about how stable can it go from wafer to wafer, field to field. How defect performance we haven't talked about. That's also something that is critical for nanoimprint. Overlay requirements.
Is he gone?
So I wouldn't be able to have a direct comparisons on this.
Yeah, sorry. You were gone for a little bit. Can you repeat, Henk, please, the last two phrases?
Oh, just to mention that indeed, nanoimprint has definitely a field there as well for waveguides printing, and it's a matter of comparing the different performance capabilities in terms of defects, overlay, throughput that eventually brings you into the cost discussion, but also a lot about the stability.
Guys, I think you are frozen again.
On a number of aspects of stability. Sorry.
Yeah, no, it's okay. No worries, no worries. Yeah, I would like to know. I mean, Enrique Frutos from Alcyon is in the room. I would like to know if you have a comment about these kind of things. Enrique, you are around? Can you unmute?
Yes, I am.
Okay.
Good afternoon, everyone. You are asking me about printing and sorry, which was the question?
Yeah, if you have an opinion here, because I mean, it's the kind of things that you are looking for too.
Sorry, which kind of things? We are making designs for photonics.
Yeah.
And the question is about the feature size, isn't it?
Yeah. Yes.
Well, for us, it's pretty critical, not at the level right now in electronics, but yes, we are working with software wavelength designing, and that's requiring a pretty small feature size. Then that's becoming interesting for us as we can get designs in foundries, which not them all are offering for photonics.
Yeah. Okay. Thank you. Yeah. Thank you so much. So, I would like to say, the precision in lithography degrades significantly, and sometimes it's matter to reach the proper tears of is the losses are occurring primarily in the packaging or the co-packaging. And someone that actually help with these kind of things and really know about that is George Ong from Senko. So George, the floor and the attention is all yours.
Got to find my unmute. Hello, everyone.
Yeah.
I'll share the screen. Can everyone see that okay?
It's not in presentation mode yet.
Not yet, not yet. There we are.
Clear.
All right, well, thank you, everyone. It's a pleasure to be speaking on behalf of Senko Advanced Components today. I'm George Ong. I'm an Associate Senior Technologist at Senko, and I'm going to be discussing how we can best enable co-packaged optics at scale with the solutions that we're offering. To begin, I want to start with a brief outline of co-packaged optics before I lead on to the challenges that CPO brings to manufacturing and how we can look to overcome them. So the demand for higher bandwidth and lower power consumption is driving innovation on board, as we've seen today, especially in the context of future AI workloads. It appears that optical pluggable transceivers have reached their limit in regards to front plate density. And CPO is an attempt to exceed this and overcome this. Co-packaged optics increases bandwidth by exchanging these faceplate pluggable transceivers for higher density connections, whilst simultaneously moving the electro-optical transceivers adjacent to the source of the electrical communication. You can see that in this figure here. As we move those electro-optical transceivers towards the ASIC, we're reducing that electrical pathway that offers up higher power efficiencies. Now, as an example of such a co-packaged optics system, I'd like to present this Marvell network, switching network. And you can see that the slide shows multiple optical engines integrated onto a single ASIC module. Now, with each of these connectors representing many in and out channels, the total bandwidth is increased by the shoreline density that you can achieve at that location A on the figure. The complete CPO solution, crucially, requires the development of optical interconnects capable of low-loss coupling from the photonic engine's PIC into optical fibers. So the rest of the presentation will outline the challenges in designing these interconnects and also how the manufacturing supply chain and workflows can help to inform those designs to ensure that we can get scalable co-packaged optics solutions. So this is the main component of the interconnect. It's the fiber array unit. Now, this is an example of one, Senko's metallic PIC coupler. Now, this is where optical fibers are arrayed using precision V-grooves. Metallic micromirrors take the light from the optical engine and redirect it into the optical fiber array. Now, from the pictures in the top right, we see that the optical path is dependent on the FAU positioning relative to the PIC. These tolerances are reduced by using expanded beam systems, as we've discussed previously today, and are seen as another platforms such as TSMC's COUPE. But this in turn produces stricter angular tolerances. Overall, this demonstrates the first challenge. A multi-degree of freedom active alignment is required to ensure a high performance of any FAU design. And integrating this alignment as early as possible is preferred to maximize the scalability. But as the picture in the bottom right suggests, we want to delay the cable attachment until the end to avoid dangling fiber optics during packaging. So what's the solution to this? Well, this is where detachability offers a primary solution. If you consider attaching a receptacle to the PIC, that's demonstrated by the gold item on the bottom there. If you attach this receptacle at the PIC at die or even wafer level with high throughput, then consider connecting a cover plate to your FAU and aligning that to the receptacle by passive alignment features. You can offer a connectivity solution that is repeatable and interchangeable. With the solution, active alignment of the receptacle to the PIC is done in a more scalable part of the workflow. Fibers aren't left dangling throughout the packaging procedure, and also expensive CPO systems aren't bottlenecked by the failure of one optical connection because you can just simply replace it without difficulty. Now, whilst we've removed the need for active alignment during the cable attachment process, there's still motivation to improve active alignment techniques. They must be fast, definitive, repeatable, and suitable for high channel count connectors of greater than 36 up towards 72, and in 6 degrees of freedom. If you think back to the CPO module we discussed earlier, there are 32 optical engines in one module, and once we start to break down the manufacturing workflow, the importance of active alignment becomes clear. So active alignment is necessary for wafer scale probing of the PIC to ensure you know which dies are good before moving on to assembly. It's also needed for optical testing of the engine and for this proposed receptacle attachment that allows for the detachability down the road. Later on in this workflow, of course, you've got the electro-optical testing of engines, the module level, the cable attachment, which is now thankfully done passive, and then the testing of the tray totally. As you can see, thinking back again to that Marvel Senko network switch from earlier on, if one detachable FAU can connect 72 optical fibers, and there are 16 engines, and 3 active alignment operations here, that's around 100 active alignment operations throughout the supply chain. So the importance of this process can't be understated. Now, a new multi-channel alignment approach is going to be discussed in the next presentation, which is convenient with Justin Bressi. But for now, I just want to underline the main points of that detachable solution. So detachability enables the new CPO supply chain because it delays that cable attachment to the final end. And detachable connectors, they need to be repeatable and interchangeable, which means they need to be both precise and accurate. And we achieve that using this active alignment. And that's all from me. Thank you very much for the time. And if you have any questions, I'd be happy to answer them.
Thank you very much, George. I think that you already called for a very provocative question, and I know that the question is already on the auditorium. So, Philip, be kind. Here we go. Philip Friedrich, Keystone Photonics.
Yeah, so we're sitting in the same value chain. So we're basically doing the probe pick way for the double-sided, and then I guess Senko goes on. I have a question on this. I mean, you said, if I understood you right, you're saying that the seat, or how you call it, SEAT, is aligned actively. Did I get that right?
Mm-hmm.
But then you say next to it HVM, which usually says high volume manufacturing. But active alignment and high volume manufacturing, that it doesn't work together.
But so I think what we're trying to show is that there's active alignment steps regardless of your process flow. I mean, you need to check the wafers are functioning, and to do that, you need to optically couple, which is active alignment.
That's true, yes. But step 3, the receptacle attachment, that doesn't need to be active. That can be passive.
In order to get the best performance out of your optical interconnect solution, you're going to want to actively align. And we talked about the Vanguard solution earlier on. While that's not actively aligning the components together, it's still actively tracking the 2 input and output ports.
Yeah, but active alignment means operating or shining some light on the device. Yeah, no. What I'm just saying, there's been decades of research, IBM, etc., on passive alignment, right? And that somehow worked. And I don't understand why suddenly one has to drop back to some active alignment on a seat. I mean, you can have some, I don't know, grooves or whatever on the wafer. And we do the testing before that.
Grooves work sometimes if you want fiber optics, but that's going to reduce your front density because you're going to have that.
No, like to place the seat. I was just saying some fiducial or some mechanical alignment marker. I don't see how this can be active alignment and at the same time suitable for volume production. So is that just an intermediate step, or is that really your strategy?
I think it can be ready for high volume manufacturing if you improve the steps. As we see, active alignment is already used in these workflows already. And the idea of keeping it in the workflow that uses it, i.e. at the foundry scale, it enables that to be part of the solution. I understand why you're pressing.
Yeah, I mean, I see all these foundry approaches that were before the V-grooves and so on. I mean, my understanding is that this whole coupe process and so on is trying to replace that and make it better, right? So not have the slow alignment that bottlenecks everything, but just to do that fast and wafer level. So I'm very surprised to see again active alignment in this, and I think we should work on making this passive and test the chips before properly.
And I think we should work on that together. Gentlemen, we will all meet definitely once again at the Brussels to continue this lovely conversation. But yes, Philip, you asked a question which I think was on everyone's mind. Meanwhile, thank you so much, George. And I would like, as you already gave a teaser, to introduce into the conversation your partner that supported you with the active alignment. And it's Justin Bracey from Aerotech. Justin, are you with us?
I am.
Perfect. Then please share your screen and the attention of everyone is yours.
Awesome. Thanks for that. Are you able to see this slide?
Yes.
Great. Well, thanks, George, for the great presentation and the warm introduction. So my name is Justin Bressy. I'm a business development manager with Aerotech. And today I'm here to present PicAlign, our multi-channel active alignment architecture that we've developed in collaboration with Senko and Santec to address some of the active alignment challenges that George mentioned in his presentation. So a little over a year ago, we started working with Senko and Santec. As this audience is well aware, active alignment is a big challenge throughout the co-packaged optics value chain, as well as other silicon photonics processes. Really, active alignment's a big challenge, and really these devices can be sensitive in, as George mentioned, both translational and angular degrees of freedom. So often sensitive in 6 degrees of freedom, particularly for grating coupling devices. And so Senko came to us with this challenge because current methods of active alignment tend to use like legacy algorithms that were optimized and developed for aligning single channels. And when you have a multi-channel device, whether it's 8 channels, 16 channels, and higher channel counts, that high dimensional cost space becomes very complex very quickly. And so we really set out to develop a new approach that would basically make these alignments more effective, both in terms of the alignment quality and the alignment speed. So as shown on the slide here, Aerotech's a provider of nanometer level precision motion systems, and that's needed for these alignments because, again, these devices are sensitive to often sub-micron misalignment, especially when you've got only a 9-micron core fiber. If you're misaligned by a single micron, you can see meaningful power loss. Santec is a provider of high-power stabilized light sources and multi-channel optical power meters, as well as other optical instrumentation. And Senko, you just learned about what they bring to the table. And so we set out to develop a new solution for these multi-channel active alignments. And that's what's shown here on the right is our PicAlign architecture. And I do want to highlight that the architecture is actually mechanics agnostic. This is just the initial system that we built as a technology demonstrator and for our test purposes, but ultimately you could use any configuration of positioners and mechanics. It wouldn't have to necessarily look like the mechanics you see here on the screen. So with that in mind, basically PicAlign is an architecture that uses multi-channel simultaneous monitoring to perform these alignments, again, much more rapidly and more effectively than old methods. And we do that. One of the first innovations of this development was that we were using multi-channel power meters from Santec and interfacing those directly with Aerotech's motion controller to monitor multiple loopbacks or multiple input and output channels simultaneously. So the system you saw on the previous slide uses, we were using 8 power meters in that case. So we're monitoring 8 channels. You could do more or less depending on your application and the available number of loopbacks or other structures you can actively monitor. But that all being said, we monitor all these channels simultaneously and search the high degree of freedom search space, which in our case was 6 degrees of freedom, although we believe it could be scalable to beyond 6 degrees of freedom. And I don't have time to go into that in too much detail, but really if you're aligning more than 2 devices, let's say there's 3, well, in that case, you basically have 2 6-degree of freedom alignments happening together. That becomes a 12-degree of freedom problem. So this algorithm is scalable beyond 6, but in our test cases, we were looking at all the channels of the device simultaneously while searching this high dimensional search space. And we then deployed what we're calling the custom objective function, which is built into our algorithm. And what this does is it mathematically combines the different power levels to represent you could think of it as an alignment score for a given coordinate in your search space. And so, at the most basic level, you can take an average of all the power levels, but what you can also do is do a weighted average or do some other kind of mathematical combination. And this can be beneficial when needing to align, say, like a polarization maintaining fiber, for example. That's the alignment's more critical for that channel than for some of the others. And so it allows you to define what an optimum alignment looks like for your specific device. It also allows you to set thresholds along the lines of, all channels must exceed X power level, and that kind of thing. And so what this enables the user to do is very rapidly search a high dimensional space, find an alignment optimum for a multi-channel device, and do that very quickly. It also provides more simplified integration because we have worked with Santec to integrate all the optical instrumentation into this architecture. So we've identified this as a major challenge, pain point in the industry, and we think that PicAlign is going to help alleviate some of those bottlenecks and really improve this process in a variety of applications, including test and manufacturing applications. So with that, I think we're just about out of time.
It's okay. We're still having a few minutes. Thank you so much,
Great.
Justin. I would be curious to ask, when you already speaking about such high levels of precision for the alignment, what are your limits? Is it the stability? Is it calibration, vibrations, or how good the metrology is to tell you, I'm in the right position?
So that's a good question. I would say that the positioning systems in this case are capable of at least an order of magnitude smaller position than what is typically needed for these applications. So the positioner I showed there is down in the single-digit nanometer ranges, and so that's not usually the limiting factor. In terms of speed, the limiting factor is often how dynamic the system can search, how dynamically the system can search the space. And so that's why we chose serial kinematics in this case, as opposed to parallel kinematics like a hexapod, which is not typically as capable in terms of the dynamics. That being said, the limits, I guess what we're seeing, stability can be a challenge for sure, although the Santec light sources and power meters are highly stable, which allowed us to maintain long-term stability. We also had the system on air isolation in our lab to ensure that vibrations from outside sources were rejected by that air isolation. So there's a number of different challenges, but there's methods to addressing all of them if you build the system in the right way.
Okay, thank you for the comment. And there's a question also from Laura from Vanguard Automation. Laura?
Hi, I just maybe you can't comment, but if you could comment on how long would a typical alignment sequence take for the
Yeah.
PicAlign?
So some of our initial results, we're seeing alignment times. It really depends on how long, or sorry, how precisely you need to get within like the theoretical optimum, but we're getting within about 0.2 dB of the maximum transmission between the devices in about a second or two, and we're seeing within 0.05 dB of that maximum in a few more seconds. So think like 7 to 10 seconds. We still think we can improve on that as well, but ultimately we're getting very, very close to the identified maximum very rapidly. And we identified those maximums in our lab by doing basically like brute force searches of the search space to characterize the entire high dimensional search space and really understand, okay, where is that true optimum? And then run the algorithm to see how quickly we converge to that.
Thank you. Laura, you're happy with an answer? It was a very detailed one.
It was a good answer. I think we can chat offline now.
Great. That's what I wanted to hear. Thank you so much, Justin. Thank you to all of us, to all of my speakers. We are wrapping up. I would like to once again thank you for being here, for sharing your expertise. It was a pleasure. I hope that I see most of you, if not all of you, in the in-person meeting in Brussels, where we continue to discuss the topics like the passive low loss fiber attachment, detachable fiber attach, and Senko is on the panel, where we continue to discuss with the lithography solutions for this for the advanced packaging with ASML, where also Leron presents more of the details into what NVIDIA is up to, so that maybe Philip will finally get a question, what's the roadmap? Probably not, but let's hope. Anyways, with this, I would like to thank you once again and close meeting with also thanking my team and the entire Optica, especially our Optica corporate engagement that made this possible. Thank you for your attention and hope to see you in person soon.
Thank you.
Thank you.
Thank you.
Thank you very much. I would like to kindly ask our I team to